We'll continue reviewing linear algebra. The next 3 questions are about subspace. So a subspace, we have 3 of these properties: closed under addition, closed under multiplication by scalar, and the 0 vectors is in there. So that those 3 properties. So a subspace should have all 3 of these properties satisfied. Alright, now let's look at some example first. Determine which of the following set is a subspace of P of n for an appropriate values of n. Alright, so we have a space of all the polynomial n, meaning the degree is n, with degree at most n. So if n is 3, we have a qubit, a quadratic, or anything less than that. So the set of all of those polynomials of degree 3 or less will belong to P3. Right, now let's look at this. So all polynomial of the form, in this case, where a and b are real numbers. Well, so if we choose a to be 0, b to be 0, and when we look at this, we have no t here. So let me rewrite this. So polynomial here. The reason I write the boldface here because this is treated as a vector. So we said a plus, there's no t, you can write like this. So if we write this as a vector, we have coefficient of a, 0, and b. So the set of all the vectors in this form. Now, the vector of this form, if we choose a to be 0, b to be 0, so the first will be satisfied. And if we choose this will be closed under the first properties, it has the 0 vector. The second is closed under addition. If you have the first plus the second, when you add them, we still have the first plus the second. The second component is always 0. I will write this a1, 0, b1. If we add that with a2, 0, b2, of course you're going to have a1 plus a2, 0, b1 plus b2. It still have 0 in the middle. So it's 0 is in there, because if we can choose a, where a equal to 0, b equal to 0, the vector is closed under the vector 0 is in there, and it's closed under addition. Now closed under multiplication. If we multiply a number into it, we still have this form. So the first one's good. So this is a subspace. It have all 3 of these properties checked. Right, next. All polynomials of degree exactly 4. Now that is the problem here. Degree exactly 4, meaning that if we write we have to have something of the t to the 4th, where a cannot be equal to 0, right? Because if we don't have the 4th degree term, we don't have the highest degree as the 4th, we don't have the t to the 4th, we will not have the polynomial of degree exact 4. So a cannot be 0. Now if a cannot be 0, the 0 vector cannot be there. So we have to have a vector of all zeros, but the first one cannot be 0. Therefore this one fails. So this is not a subspace. Next. All polynomial or degree at most 4. That's okay, at most 4. So that's good. Could be 4 or less. So potentially 0 in there. But it has all positive coefficient. Now if the coefficient being positive, it cannot be 0. And we have to have a 0 vector in there. And also if we have all the positive, if we multiply by a negative number, all of them turn into negative, and so it will not close under addition. So this one fails as well. So because of that, only the first one is true. So we're gonna go with this. Right. Next, let H be a set of all the points in this form. Determine whether H is a vector space. If it is not a vector space, determine which of the following properties is failed to satisfy. Right? So contain a zero vector. Now if we have the vector of the form S, now I'm talking about the first one here, S and S minus 1, can it be 0? Well, if that to be 0, then S had to be equal to 0, and S minus 1 equal to 0. So we have to have S equal to 0 and S equal to 1 at the same time, which is not possible, right? So this cannot be equal to a 0, 0 vector. So no, that doesn't work. Now go to B. Close under vector addition. So meaning, let's say we have S1, S1 minus 1. Let's say the vector in that form. Then we add S2, S2 minus 1. If we add them, what do we get? S1 plus S2, which is good. And then when you add these two, S1 plus S2, and minus 2. Well, if we look at the form of this, all the vector in this form of H have the first component and the first component minus 1. He will have the first component minus 2. So this entry here, because of minus 2, cannot be in H. So we have an element in H, another element in H. When you add them, we have another element that is not in H. So that is not closed under addition. So it fails. So we start with something in it, combined with another one in it, we have something else outside of it. So it's not closed. C. Close under multiplication. So if we have times K times S minus 1. So this is a vector in H. We multiply by K to it. We have KS and KS. Remember, we have to distribute. Now, this is not the form that we want. We want the first component, and then the first component minus 1. This is minus K. So once again, the result after multiplied by K is not in H anymore. Because of that, it fails this property as well. So we say that H is not a subspace, or it fails all of these properties. So, as I said, determine which of these properties it fails to satisfy. So we say all 3 fail. All 3 fail. Right. Next, we can't do the same thing, but this time we have S and 3S and T. So we checked A. Can this be 0? Zero vector, this one has 3 components, so that's 0, 0, 0. Well, now, if this is 0, then S has to be 0, 3S has to be 0, and T has to be 0. Well, this just requires S to be 0 and T be 0, which is good. So this property is satisfied. So that's good. The first one's okay. Next, is this one closed under addition? So we check the vector in this form. Let's say S1, 3S1, and T. Now we add with S2, 3S2, and T. Let's say T1, here T2. So when we add them, we have S1 plus S2. And then when you add the middle components, we can factor out 3. And then we have T1 plus T2. Now if we look at this vector, when we add them, the middle component is 3 times the first one, and the last one, it doesn't matter. So in this case, yeah, so this is in H. So this is closed under addition, so this one is good as well. Last one, we verify if this one closed under multiplication. So take K times S, 3S, and T. So we have KS, 3KS, and KT. Now, the middle component is 3 times the first one, and the last one is something else. So that's good. This is also in H. So we say this one is closed under scalar multiplication. So we can say all 3 of these are satisfied. So all 3 properties are satisfied. Right. Next, determine whether the following vector U belongs to the null space of A. Well, the null space of A. Let's just write some definition. The null space of A is all the vectors that, when you multiply to A, we have a 0. So we say X in null space of A, just say NUL of A. If we take A times X and we have a 0 vector, meaning X is a solution of the homogeneous system. So here we have the vector, so all we do is just take A times U to see if we have a 0 or not. If it is, then yes. If it's not, then no. Very straightforward, right? So just take A times U. Times U. Just going to use a calculator here, that'd be quicker. -2, -3, -5, -4, -2, -6, 3, -2, and 3. Right, multiply by vector 3 row 1 column. Oops. -1, -1, and 1. Right, so when we multiply we have 0, 0, and 2. Now this is not 0, so meaning this is not a solution to a homogeneous system. So we say the vector U is not in A. So we just say U is not in the null space of A. Find and explicit description of null space of matrix A by listing the vector that span the null space of A. Well, easy. So pretty much we just solve the equation, solve the homogeneous equation. So null space of A, meaning that it is the solution of homogeneous system. So all we do, we're just going to solve this. Take A times X has to be equal to 0. So we just construct a anometric matrix 1, -2, -5, and -3. 0, 1, 1, and 2. And then the right column is just 0. So we do that. And we do reduce row echelon form. Right, so that's what we have. 1, 0, -3, 1, and 0, 0, 1, 1, 2, and 0. Right. So we solve for x. So we can say this is x1, x2, x3, and x4. And the pivot will be here and here. So we write out x1 minus 3x3 plus x4 equal to 0. And then on the second, we say x2 plus x3 plus 2x4 equal to 0. And x3 and x4, there's no pivot on it, so we say they are free. Right. Now if we want to solve for all of the x, we will write the solution as follows. X is the vector that has 4 components, x1, x2, x3, and x4. The first component, if we want to solve for x1, we move this to the other side. 3x3 minus x4 and then negative x3, negative 2x4, x3 is 3, x4 is 3. So now, if we group all the x3 together, actually we can put all the x3 together, if we factor it out, we will have the vector of 3, 3x3, negative 1 of x3, 1 of x3, and 0. Then plus for x4, negative 1 x4, negative 2 x4, no x3, and 1 x4. So what we have here is the two vectors here that we say will be the basis for the null space of A. So the answer would be the two vectors right. So pretty much we solve the system, the homogeneous system, and find the solution and write that in the parametric form like this, and then we can have the vectors. Next, determine which set of the following vectors are linearly independent. Well, the way to determine that is just use the Wronskian. Here we have three vectors here. So we just say the Wronskian will be equal to P1, P2, P3. We just have a square matrix, so we have the first derivative. So P1 is 1. If we check derivative, we have 0 and 0. P2 is t squared. If we check derivative, 2t and 2. P3 is 2 plus 3t. Take derivative, it will be 3 and then 0, right? And then we just find determinant of this. If it is equal to 0, then it's not. If it have equal to 0 for some value of t, they are not linearly independent. Right. So here what we can see is if we expand everything on the first row, actually the first column will be good. So I will write 1 and then cover the row and the column that containing 1, because that's how we do find the determinant. And then the order will be just 0, 0, 0 something, and then 0 something. So that's good. The rest is 0. That's what we have here. So we have 2t times 0, so that's 0, and that gives us negative 6. Now, since the Wronskian is not equal to 0 for every values of t, they are linearly independent. Yeah, just like that. Right, next, Wronskian for this problem. Once again, just have P1, P2, P3. There are three vectors here, so we need to have the first derivative and the second derivative. So that we will have a square matrix to find determinant. Right, the first one is t. Derivative of t is 1. Derivative of that is 0. The next one we have t squared, so 2t and 2. The last one is 2t plus 3t squared, so be 2t plus 3t squared. Derivative will be 2 plus 6t. Derivative again will be 6. Now, 2 by 2 determinant. I will go by the first column. Start with t. Cover the row and the column that containing t. We have 2t, 2 plus 6t, 2 and 6. Next we minus 1. And cover the row and the column containing 1. We have t squared, 2t plus 3t squared, 2 and 6. The last one 0, so it's just 0. Right, so determinant t, that 12t minus 4 minus 12t. Right, next, minus 6t squared, minus and then 6t squared minus 4t minus 6t squared. Just find the determinant, really. So, the 12t cancel. We have negative 4t and 60 square cancel out. That plus 4t equal to 0. So because of 0, we Wronskian equal to 0, we say the vectors are, on this case, the polynomials are linearly dependent. Right. Same thing on the next one. Just find the Wronskian. One, 0, 0, t square, 2t, and 2. This is P3. Take derivative against 2. Right. Now we expand using the first column. So at 1, cover the row and the column that contain 1. We have that 2t, 3 plus 2t, 2 and 2. So, and then we have 0, 0, of course. That doesn't give us anything. So just find the 3 by 3 determinant. We have 4t minus 6 minus 4t. So this is minus 6. So this is not equal to 0. So it is linearly independent. Times 10. Next, determine whether V1, V2, V3 is a basis for R3. Well, first of all, when we look at this, we see there are 3 vectors. So the basis in R3 require 3 vectors. So that's good. We have 3 vectors. So all we need to do is just make sure that the vectors are linearly independent, or the vectors are spanned. So the basis has 2 properties, 2 boxes to check. Usually, number 1 is linearly independent. The second box, they have to span R3. Now, usually we check those 2. However, in this particular case, we have 3 vectors. So if we have 3 vectors, we have R3. So if we have 3 vectors, we only need to check one of the 2 boxes. We have 3 vectors here corresponding to this 3. So we only need to check one of these 2 boxes. And the linearly independent is the easiest one to check. We just use the determinant, right? So let me write the reason behind this. For R3, we need 3 vectors to be 3 vectors in their basis, in its basis. And the vectors only need to satisfy one of the 2 because we have the same 3 number as that. So we need 3 vectors in its basis, and the vectors only need to satisfy one of these properties. I should say, when it satisfies one, it will satisfy the other. So we only need to check one properties. It should be. it then would satisfy the order. Right, that should be they because they're three vector. Then they then satisfy the order property. So we have only check one of those properties, the order will be good. If one of them is good, both of them will be good. Right. So we have the vectors here, so all we do is just find the determinant of v1, v2, v3. We just stack all the vector in column. So we find determinant. Right, so it is equal to 0. That means they are not linearly independent. So this first one failed, so it cannot be the basis. If we check the first one, it will be check the second box as well, because we have three vectors in R3. So the answer, this is equal to 0, so we say linearly dependent. Right, so that's pretty much it. Right, I will do the next two problems together. So pretty much what we have is a matrix, and on the test we may or may not have the matrix in reduced row echelon form. Actually this is just in echelon form, right? So for the matrix A is given a matrix equivalent to this. So if we do the row echelon form, we have this, because we have the pivot here, here, and here, and this is the echelon form. Now the next two problems we are given that. So we have the matrix and the row echelon form of it, right? On 56, question asks for the basis for the column space. So for column space of A, the second one for the row space of A. So if we write it out, it will be row of A. We're going to find the row space of A. Well, it will be very easy. Put the matrix in the calculator, do reduced row echelon form or echelon form. Either case. This problem, they give you the row echelon form already, so we don't have to do anything. So when we look at this, we see that the pivot in the first, second, and third. So the column space, the basis for the column space of A will consist of the vectors where the pivots are. So I will write here basis for column of A are columns in A where the pivots are. Right, so when we see the pivot on first, second, and third, so just going to write the first, second, and third column. Notice that it has to be the vectors in the original column and not in the row echelon form. So we just have -1, 1, 2, and 3. -3, -2, -4, and -6. 7, -7, -9, and -11. So we have these three vectors. The vectors where the pivots column are in the reduced row echelon form, where the pivots are, I should say, in the reduced row echelon form of A. In this case, of course, we can also use just row echelon form of A. So this is a column in the original matrix A, where the pivots in the reduced row echelon form of A. So watch out for that. Next, for row space of A, let me just write what we're looking for here. So basis for the row space of A, I'll just say capital I. Row space of A. Of course, if it is a row space, it will be rows in. Now the difference here is we're going to look for the reduced row echelon form of A. So we look at this matrix and not this matrix. The matrix when we have done the reduced row echelon form or echelon form. The rows, I would just say the pivot row will be good enough. Right, so we already done the echelon form already given, so we just look for the row where the pivots are. The last one 0, of course, cannot be in the basis, so we just write those 3 rows, and that is it. So make sure you know how to find the row space, how to find the basis for the row space, the basis for the column space, and the basis for the node space. Let me just go back to that quickly. Right, so this is how we find the basis for the row space. This is how we find the row space for the basis for the column space, and this is how we find the basis for the node space. So should be able to find the basis for all of those bases, those spaces. Again, the node space, column space, and row space. Right. Timestamp. Right. Let H be this matrix. I'll find the dimension of the subspace of H. And we look at this, we say there's A, B, C, D, well, the dimension 4, right? And there are 4 vectors, 4 components. Well, be careful with that. We just have to write this in the matrix first. So if we're going to write this in the matrix, there's 1A, 3B, no C, and 4D. And then 3C, 1C, no A, no B, 1C, and 1D, -3, -9, 4, and -8, 0, 0, -1, and -1. Right, so we write that matrix represent by that. Well, when we look at this, we won't be able to tell, but if we do the reduced row echelon form, we will see. Notice that this is just a matrix and not the augmented matrix. The augmented matrix will have the row of something on the right side. right? And we have that. So when we do this, we see that there's only two pivots. Right? So we really need two vectors for that. So the dimension is that, of course, it's just 2. Yeah. Right. What's next is more important. So when we look at this matrix, find the dimension of null space and the column space. And this is very important. Dimension of null space and the column space. So what we have is just put in matrix, reduce the echelon form, and that will be it. We go from there. Right? The good thing is when we look at this matrix, well, it is already in the row echelon form. So we should note that we have the pivots here, here, and here. So we say this already in row echelon form. Right, so just go from here. Right, now remember the column space is where we pick up the column. Originally not the one in reduced echelon form, but here we have 3 columns. So we said the column space so the column of matrix A has 3 vectors where the pivots are. The basis for column of A has 3 vectors. Or to say need 3 vectors. So in this case we say the rank of 3. And the null space of A is the space of the solution of homogeneous system. We have 1, 2, 3, 4, the 4 free variable. So the null space of A will have 3 vectors in these spaces. Or we say need, okay, I can write the same way. Have just write exactly as that. Because of the 4 free variable. So the column of A need 4 vectors for its spaces because of 4 free variable. So that gives us, that is the nullity of A. And that is the theorem. When we add them together, it will be equal to the number of columns. In this case, sorry, it should be 4. When 3 plus 4 is 7. Right, so to recap, the rank of A of a matrix is equal to the number of vectors in the basis. in basis for column space of A, meaning that it will be equal to the number of pivots. That's the first important part, which is the dimension of rank A is the dimension of the column space of A. Right, next, the nullity of A is equal to the number of vectors in the basis for the null space of A, which is equal to number of free variable. Right, let's keep that in mind. And when we add this together, we will have the same as the number of columns. Right, so that was that. The next two I will do together because it asks for the same thing. Right, so this question asks for the null space and the column space and the row space for the following matrix. So actually the question should be find the basis for right. So all we do is just have the matrix and do the reduced row echelon form, and we go from there. So we have the matrix A here. So just do reduced row echelon form. Actually, this matrix is in row echelon form already. We really don't need to do this. We just work with this because this is already in row echelon form. Right, just convert this to fraction so it's tidy up. Okay, a little. Oops, sorry. Right. So here we see there's a pivot here and here and here. So there will be for the column space of A, there should be three vectors, three column vectors corresponding to these three pivots, and the vectors come from the original vectors. So the basis for column of A is 1, 0, 0, the first one, the second column, and then the third column. That is those spaces, the basis for the column space of A. For the null space, for the row space of A, I will do the easy one first. We'll just look at this, and there are three pivots, so we just have to write all three the pivot row in the result here. So the basis for the row space of A, 1, 2, 0, negative 2, 0, 1, negative 1 third, 0, and 0, 0, 0, 1. So we just do reduce to echelon form, and the column spaces where the pivots are, we pick the original column from the original matrix. For the row space, we just pick all the row, the pivot row in the reduced to echelon form. Right, now we go to the node space of A. For this, we just need to solve for the homogeneous equation. Right. Actually, we don't really need to enter the last column here, right? Because all the zeros, the last column is always 0, so we don't need to just do this. Reduce to echelon form of the left hand side here. The right hand side is going to be 0. So basically, we're just going to have exact thing on the left hand side here. So we solve for x. So this is x1, x2, x3, and x4. The pivots here, here, and here. So those are the pivots. We can say x1 plus 2x2 plus minus 2x4. Equal to 0. X2 minus 1 over 3 x3 equal to 0, and x4 is equal to 0, and here of course we don't have the pivot on x3, so x3 is 3. So if we write the solution, it will be as follows. Wait. Sorry. Yeah. Let I check. This should be 0, right? Okay. I completely didn't copy everything. Right, sorry. Right. Right, so it was that. Now, the column space of A is still the same, so that's good. The pivot is still on that, but the row space not right. 1. It should be the row in the end result. Sorry about that. Yeah, just that result, this matrix here. Right, reduce to echelon form. Let's do this again. x1 0, 2/3 0. Okay, that's good. So, because when you write this, there should be something not right. Because only if a free variable x3, we should have all the basic variable x1, x2, and x4 in terms of x3 here. Right, let's write the solution. X equal to x1, x2, x3, and x4. x1 is 2/3, x3 1/3, x3 is 3, and x4 is 0. So if you factor out the x3, we have 2/3, 1/3, 1, and 0. So the basis for null space of A is this vector here. If we want to choose a better one, choose x3 to be 3, multiply all of this, then we don't have to deal with fraction. So that's a better way to write that. But anyway, if we just want the basis for it, we're just going to say it, this vector here, 2/3, 1/3, 1, and 0. Right? So that's how we find the basis for the column space of A, the row space of A, and the null space of A. Right? We have another one here. So first we do is finding the reduced to echelon form of it. Right, let's convert this to fraction. 1, 0, 46/11, 0, 1, 3/11, 0, 0, 0. Right? So the pivots here and here. So for the column space of A, this is where the pivots are. First and second column. We're going to use the original matrix for it. So these two vectors, these two columns, are basis for the column space of A. For the row space of A, we're just going to take these two rows, the two pivot rows. And then next we go to the null space of A. Find the basis for null space of A, which involves solving the system equation of the homogeneous system. So we have this matrix. Just make sure I enter the right values. Right. And then this is a romantic matrix. So we'll have 0 on the right hand side. And reduced to echelon form, we don't have to do this again. It will be just this one on the left hand side. So we write x1 pivots here and here. X1 minus 46 over 11, x3 equal to 0, x2 plus 3 over 11, x3 equal to 0, and x3 3. So we have x equal to x1, x2, x3, x1, just move that to the other side. We have 46 over 11, x3, 3 over 11, x3, and x3 is 3, so just itself. Now factor out x3, we have 46 over 11, 3 over 11, and 1. And that will be the vector for the basis of the null space of A. Right. So that is how we find the basis for the column space, the row space, and the null space. Right, next, if A is a 5 by 9 matrix, what is the smallest possible dimension of the null space of A? So think about this. We have the null space, the A, 5 rows, 9 columns. So number of rows, number of columns. So 1, 2, that too much, but we're going to have 5 rows. Right. So let me just write this. A is 5 by 9. So A has 5 rows and 9 columns. Because it has 5 rows, we have at most 5 pivots. And then 9 columns. If 5 of them are pivots, at most 5 of them, that means 9 minus 5, at least we have 4 free variables. So the dimension will be at least 4. Because dimension of null space of A is the same as the vectors in the basis for the null space of A. So pretty much, once again, the 5 rows minimum, the 5 rows, the maximum of 5 pivots, meaning that at least 4 of them are free. So so the basis for the null space of A is 4, at least 4. So that would be the dimension of null space of A, be at least 4. That should be B. I will stop the video here and we'll continue in another video to review linear algebra.